Thank you. Thanks all for coming. So it's a long title, but I'll try to break it down piece by piece. And can you all hear me OK? All right. So the setting of this talk is going to be that of prediction on infinite binary sequences. So we think of this string x as being revealed to us piece by piece. And our goal is just to make some kind of interesting prediction about the future based on the past, based on our observations so far. And so in general, we're not going to be placing any computational boundedness assumptions on ourselves. But as we'll see, the algorithms that we describe are going to be simple. And so the setting of binary sequences as opposed to ternary or so on is not really important. But I think with a suitable level of abstraction, this can be taken as representing a variety of interesting real-world phenomena we'd like to get a handle on, from movements of a stock market up and down to sun and rain, and to other kinds of interesting prediction problems. And of course, our question is, given that we'd like to make interesting predictions and use them to govern our affairs, what kind of assumptions do we need to make on the sequence x in order to get interesting predictions? And the message of this work, amplifying on past works in this line, is that we can get by with surprisingly weak ones, with surprisingly weak kinds and also strengths of assumptions. So the first thing to kind of clarify for ourselves is, what kind of opponent are we facing in this prediction task? So we know who we are. We're algorithmists or statisticians, or we're bringing a variety of tools to bear on prediction. But who are we facing? Probably the most natural class of predictions we could care to make is against probabilistic models, where we have some kind of model of how nature behaves, which is inherently uncertain. And this is attractive because we have such a variety of tools to bring to bear from statistics, and from Bayesian reasoning. We have these very firm normative rules about how we can update our beliefs based on what we believe to begin with and what we've seen so far. So this distribution D continually evolves under the revelation of each new bit in the sequence. Of course, the problem in realistic applications is, when do we know that our model is adequate? We start out with a simple model, and it's revised in the light of being overly idealizing. When do we know that we've got an adequate model? Well, there's perhaps some hope of learning these distributions over time and gaining knowledge that way. But even assuming that we've converged on the right distribution involves some kind of commitment that the past will, that the past and the future will resemble each other in some sense. So these are dicey, assumptions to make in some cases. And I think often the assumption that we have some known probability distribution has more of the flavor of a philosophical commitment or conviction rather than an actual, firmly held scientific belief. So, some people who subscribe to a Bayesian philosophy think that, our beliefs about the future and our uncertainties about the future are always expressible in this way. And that whenever we're revising our views in the light of new information, we're doing it according to something like Bayes' rule. But that's hardly uncontroversial. So the question is, can we get beyond this? And can we do something that will perhaps satisfy individuals who believe that nature is governed according to some known probability distribution, but which exceeds under looser assumptions, which will satisfy more people? And so, of course, that leads us to the class of adversarial models, our worst-case analysis, where we merely assume that our input sequence x is drawn from some known set A of infinite binary sequences. And so here we regard nature as truly an adversary who knows the strategy we're planning to use to do some kind of prediction, and is going to pick the worst instance for us for this task. And I haven't specified the task yet, but This applies across a variety of prediction tasks. And the point to make is that these assumptions can be quite safe if we define the set A conservatively enough. The reason being that if we regard A as a set of possible worlds and we want to succeed with good confidence in some set of possible worlds, well, succeeding against a larger class of possible worlds, which includes some blatantly impossible ones, is not really any drawback. So that's our focus. And I want to mention that there's been a variety of interesting prior work on adversarial prediction that's somewhat relevant to my work. So the first strain that I wanted to mention was that of Gales and Gale characterizations of fractal dimensions. This was pioneered by Lutz in the past decade. So what Gales are is a class of betting strategies in which, as these bits are revealed, we stake some amount of money on the outcome of the next bit seen in the sequence. And so our goal is a long-term one of reaching an unbounded fortune as time goes on. And there's different varieties you can look at here. This can be a strict increase to infinity, or it can be a gradual one where you continually dip down towards 0 again. And so depending on how you set the details, you can actually give an alternative characterization of familiar notions of fractal dimensions of sets of sequences in terms of the amount of handicap as a gambler that we need to successfully gamble on an arbitrary sequence X drawn from the set A. So in general, a fair bet is one in which if we have we have an initial fortune of X, and we go up to a fortune of Y if a 1 appears, and a Y prime if a 0 appears. A fair bet would be one in which X is equal to Y prime plus Y over 2. So we win and lose corresponding amounts. And so let's notice that you can look at a relaxed notion in which we have some scalable parameter S here. So we get a class of more or less favorable bets. And the S that we need to succeed on this class A is related to the Hausdorff or packing dimensions of the sequence set A. So quite an interesting line of work, and it has relevance to the theory of measure and dimension in complexity classes, which is kind of a special interest topic, but I think a very interesting one. A second line of somewhat related work that I will touch on more directly in my talk is that of the ignorant forecasting problem. So a weather forecaster is not expected to make a statement of the form, tomorrow it will rain. Anyone who is put up to that high standard would eventually lose their job. Instead, they have to give some kind of forecast, like 50% chance of rain tomorrow. So they're allowed to hedge their bets. But what we can reasonably expect, or hope to expect from a weather forecaster, is that on the days when he or she said 50% chance of rain, actually about a half of them ended up being rainy days. And so it looked as though the weather forecaster had access to the kind of the probability distribution governing nature, conditioned on everything we knew up to that day. Okay, so easy to achieve if we know the distribution, but the surprising fact is this kind of calibration can also be achieved by a randomized algorithm which makes no assumptions on the actual sequence of sunny or rainy days. As long as the sequence is fixed in advance and we get to use randomness, you can actually do this and look like you know what you're doing and hopefully keep your job. So, if you ever find yourself unqualified for your employment as a meteorologist, look up this paper. So both of these previous lines of work focused on some measure of long-term overall predictive success. Okay, so for Gales, we didn't care about winning or losing individual bets as long as in the net we made a fortune. And as a weather forecaster, you're allowed to be wrong, and you're allowed to indeed hedge your bets so that you're not even making a definite prediction on given days. You have to have some overall measure of competence. And so our focus, by contrast, is just to make a single prediction, a single make-or-break prediction about the sequence with as high confidence as possible. So the main task we study is called zero prediction, and we simply want to predict a single zero appearing among the bits of this sequence x. And the interpretation you can have in mind is that we have some kind of action of unit duration to perform, like crossing a dangerous highway, and we just want to choose safe conditions in which to perform this action. So we can't see safe or dangerous coming in advance, but we can observe past outcomes. Now, let's start by asking, what is the strongest kind of possible assumption we could make? What is the most structured model here, and the most simple one? And I think you'd arrive at something like the epsilon biased arrivals assumption, as I term it, which is just a sequence of independent 0, 1 coin flips, where each one is 1 with probability epsilon. And of course, you can see that the best strategy simply picks any old time and guesses 0 and succeeds with probability 1 minus epsilon. So there's no real room for learning or non-trivial inference here. But this is a good starting point to think about the problem. And of course, in cases like this, where we have some kind of maybe dangerous condition that we're trying to avoid, our best hope for succeeding is some kind of control on the frequency of this dangerous event. So that it seems like what we're really relying on here, the most important thing perhaps, is not the independence assumption, but this sparsity assumption, the law of large numbers, which tells us that in the limit, there's only going to be a small fraction, if epsilon is small, of ones occurring in the sequence. So the independence assumption is very strong, as I say. But the idea in this work, which is kind of building on previous works of this type, is to study what I would call an adversarial relaxation of this epsilon bias model. So let's just strip away most of the probabilistic assumptions and hold on to the basic sparsity of the ones in this sequence and see what we can do with that. So we start off with this structured probabilistic distribution assumption, and we relax it to some set A, which we hope just contains the support of this distribution. And if we can succeed against this larger set, we're happy. And if we can succeed against an even larger set, we're even happier, or at least we're having more fun in doing so. OK, so along that lines, let's let n sub t be the fraction of ones occurring up to time t. And let's just say that the sequence is epsilon sparse if this limiting fraction approaches something at most epsilon. So the limit doesn't have to strictly exist, but eventually we have to get as close to or below this dotted line as desired. Okay? So certainly sequences generated by our distribution are epsilon sparse with certainty. But the converse isn't true. We've added in a lot of funky strings, and we've given up all of our quantitative control on the rate of approach to this dotted line of the epsilon fraction.
So when you say this, do you really need that limit to exist?
The limit doesn't have. So I'm being informal. The limit doesn't need to exist.
You can wiggle around under epsilon. Yeah.
That's right. That's right.
Is it lim soup or is it limit?
So as stated, it's lim soup. Yes. Let's see. I always confuse these two. So let's just put it this way. Eventually, you're going to be below this line, which is slightly above the dotted line. But that's relevant to the next slide. So partly just for fun, let's try relaxing this even further to the epsilon weak sparsity assumption, which merely posits that now we don't even need to be driven to at or below this dotted line. We just need to approach it as close as you'd like infinitely often. Okay? So there are infinitely many initial sequences where the fraction of ones is in most epsilon plus something that decays to 0. So the main result then is that given any epsilon, we want to say that we can essentially succeed with the same success probability in this zero prediction task as under the epsilon biased independent arrivals. And we can't quite do that. For simple examples show this, but if you give me any slack parameter, gamma, we can succeed with 1 minus epsilon minus gamma probability. Okay? So nearly as well as under epsilon biased arrivals. Yes?
What's the definition exactly of succeeding with this probability?
Okay, so we want to predict a 0, and we only get one chance to do so. So if we make an incorrect prediction, we're dead. So if we wait forever without making a prediction, that also counts as failure. So there's only one kind of success, but there's two ways to fail.
So the strategy basically waits until some number?
Well, good. So
some number of observations that depend on the specific string? And
the number of observations will certainly depend on the specific string. So just to think about this, this statement and what it means, note that this assumption of epsilon weak sparsity is completely asymptotic. So we have no control on the behavior of epsilon weakly sparse strings on any finite initial segment. So we can't say that our algorithm always succeeds within 10 or 100 or 1,000 steps. So the rate at which we make our move towards making our prediction depends on the sequence given, and the adversary can delay us as much as they want, essentially.
But shouldn't there be, for measuring success, shouldn't there be a second quantification that if it achieves, if the sequence is such that in time t you get there? Then
Yes.
how long
So there is more detailed.
Slowdown.
There's definitely a slowdown, but you can make so it's certainly a slowdown compared to the original epsilon biased assumption where you just go immediately, right? So that's inherent, and there is something you can say about the rate at which you make your prediction as a function of how quickly the decay happens, but it's not particularly clean, and I haven't given a formal statement in the paper. But if you look at the analysis, it does involve saying like, well, if we've reached in some finite amount of time a certain level of sparsity, then we do make a prediction with some noticeable probability.
in that same time?
Yeah, within that same time, but there is some loss due to the way we chop up the sequence, as you'll see. So that part of that quantitative aspect of the time used is not as precise a statement, or as close a statement as this one. And just to be clear about the model, the adversary, as usual, is picking the worst sequence from among the class of possible attacks on our strategy after knowing the strategy that we've picked. Okay, so we have to take the minimum success over any x in our class of epsilon weakly sparse sequences, but we at least have to give ourselves the advantage that although the strategy is known, we have some inner source of randomness, okay, to make ourselves unpredictable. Otherwise, we'd be completely toast in this kind of situation. And I should mention that before getting into some of the proof, almost all the complexity, I think that ultimately this algorithm, you'll agree, is simple, but almost all the difficulty of coming up with it was dealing with this added wrinkle of weak sparsity. So it's actually significantly simpler to handle the case of sparsity, so where we strictly decay in the fraction of ones towards this limit epsilon or less. But the theorem is not, I think, not completely obvious, even in the case where we have much stronger assumptions like, let's assume that the number of ones in the sequence is finite. Okay, so let's assume that there's some finite upper bound in the number of ones appearing. So if the number of ones were guaranteed to be at most some value m, that would be easy. We would just pick some random interval of length m squared and pick a random point, and we'd succeed with very high probability. But it was a little surprising to me to find that simply having this finiteness bound is enough to succeed here. So if you'd like, as a puzzle, you can skip the rest of the talk and think about that case, or you can get the spoiler here.
And there you have to succeed with probability approaching
Approaching as close as you'd like to 1. since it's a zero, weakly sparse sequence, yes. Okay. So the first idea of the proof is just to simplify life because, as a computer scientist, I only think about finite chunks of a problem at a time. So let's divide the sequence into epochs of increasing length, where the rth epoch is chosen of length on the order of r squared. So these are determinate lengths that don't depend on the specific sequence. It's just set in advance. And r squared is chosen as an intermediate value of increase. And I think we'll see why, hopefully. And we're just basically going to have the same zero prediction algorithm that runs on each individual epoch. It's going to be suitably scaled for the increasing length. So first, how do we translate our asymptotic control on these initial segments of x into control on the epochs themselves? And the claim is that from epsilon weak sparsity of the sequence x, we can actually conclude that there's a subsequence of epochs which are especially nice for us, where the one densities, that is the fraction of ones in these epochs, are each at most some alpha, let's say, where alpha is just chosen within epsilon and a little bit. Okay, so close to epsilon. And here we're using the fact that these epochs are not growing too quickly. Essentially, this is due to the fact that when you measure the density of an initial sequence, you can kind of express it as the weighted densities of ones within each of these epochs, except that you get some loss or some fuzziness due to the fact that one of the epochs is truncated. But if that epoch is not too small compared to the sum of the previous ones, it's not a problem. So that's where we use that the epochs don't grow too fast. So an initial idea, which won't work, is to give an algorithm with the following two properties. First, we should be able to exploit the nice property of these sparse epochs. So when the quantity of ones, the density of ones in a epoch is low enough, we should be able to gain some confidence or gain some courage to make a prediction. Okay? And this will drive our algorithm to actually terminate in finite time. And so how do we get, given that we have that, how would we like to get our success probability high? Well, it would be great if we could simply have the probability of a true prediction dominate the probability of a false prediction in every epoch with some kind of multiple relating to the level of confidence, the level of success probability we want to achieve. So if we could have this equation hold here, that would achieve our goal, simply because you can rearrange this to show that in each epoch, the probability of a true prediction is at least 1 minus alpha times the probability of any prediction being made. So to the extent that we make a prediction in any epoch, we make a good prediction. Okay, and alpha is nearly epsilon, so we're happy.
So true prediction means correct prediction.
Right, exactly. Sorry. And we're always predicting zeros. You can't just cop out and say, I predict a 1. Mm-hmm. So can we achieve this? No. And the reason is not hard to see. If you think of the adversary facing down this prediction algorithm, which is randomized in this particular epoch, as soon as we've reached this epoch, we have some probability of predicting a 0 in the next step. Okay, so if that probability is greater than 0, the adversary can just throw a 1 at us. And so now all of our guesses within this epoch, all of our probability mass on guessing is concentrated on wrong guessing. And that's a problem. Okay? And more similarly, if we wait to make a prediction, the adversary can wait along with us and then do the same thing. So we can't achieve that. So then a modified goal is to, we want this minus this to be 0. But if we can't have that, we'd like this minus this to at least be small. Okay? And we'd really like it if we could somehow bound that in terms of something that depended nicely on the size of the epoch. If we could achieve this, then the defect that we see overall between having, from having a 1 minus epsilon mass of our predictions being true is only on the order of some of these terms, and as k sub r is on the order of r squared, this would be something that converges and that we could control by making constants suitably large. So that will be our goal. So now I'm going to get to the actual algorithm itself. So during every epoch, yes?
I'm not sure I understood. So in each epoch, you're trying to predict what bit?
We're trying to predict a 0 within that epoch, and I'll describe how we choose when we're going to choose to make our prediction.
Sometimes you decide to.
Sometimes you just wait out the entire epoch without making any prediction. So intuitively, if we're seeing lots and lots of 1s in this epoch, the algorithm says like, whoa, I'm scared. I'm not going to make a prediction now. I'm just going to wait till the next epoch.
So how does the adversary does what you described before, like showing that you cannot get the inequality?
How do we achieve that? Well, the adversary can, anytime we have a non-zero probability of making a prediction, the adversary can throw 1s our way. So the probability is over our internal randomness as a predictor in making a prediction. So, but the adversary knows, conditioned on what the adversary has seen so far, this strategy is just a randomized, is a distribution. So the adversary can reason about, conditioned on what the adversary has seen so far, is there some non-zero probability of a prediction happening? If so, let's just throw another 1 at it, and let's just keep killing off, the chance of a correct prediction. So we can't get that kind of detailed balance between successful and failing probabilities.
You can't get it for every epoch.
Not for every epoch, no, that's right. But we will hope to for the epochs that count. OK, so the algorithm is going to proceed by having a stack of chips. OK, so these are just tokens that are added and removed from a stack. And the height of the stack at a given time during the epoch is going to reflect some measure of the courage of the algorithm to predict that the next bit will be 0. So haven't defined that yet, but that's the idea. So high stack, high courage, and so on. Now we need some natural numbers to deal with to make things easy. So let's just approximate alpha by p over d. So, and we're continuing to think of alpha as being about epsilon, so just think of p over d as being basically epsilon. And q over d is the complement. So here's our rule. This is how our stack evolves over the course of our epoch. And it's initially empty for this epoch. So every time we observe a 0 in our sequence, we add p chips of courage to our stack. So in this case, p equals 1. We added 1 chip immediately after seeing this 0, and so on and so on. But every time we observe a 1, we're going to remove q chips. Or if we empty out the stack, we just stay empty. So how do we make predictions on the basis of this stack? Well, let's let h sub t be the stack height after observing the first t bits. First, we're going to choose some t star uniformly from among the times we could make a prediction during our epoch. We're going to let the first t star minus 1 bits pass without making any prediction. We're just going to watch the stack evolve. And we're only going to possibly make a prediction about time t star. Now, our probability of making such a prediction is going to be proportional to the stack height at that time. This is just a normalizing constant down here. That doesn't really matter what it is as long as this probability is always at most 1. And if we chicken out at this point, then we don't make any prediction. So is the algorithm clear?
You don't make a prediction,
You move to the next epoch. Yes. Yeah, right. You don't give up entirely, but for this epoch. So here are the ideas of the analysis. First of all, if the fraction of 1s is small, something that's a little bit less than P over D, then the claim is that we actually do make some noticeable probability of a zero prediction. And why is that? Well, just doing the arithmetic, a significantly larger number of chips were added than were ever removed from the stack. So that means that our final stack height is noticeable. Now that in itself wouldn't be enough to make a prediction with noticeable probability because we only choose this point with 1 over kr probability. But now chips are only added to the stack gradually. So from this, we can reason backwards and say that there was this kind of this pyramid as you graph over time, right? There was a large number of steps earlier in which the height was gradually increasing. And so if you average over that pyramid, you actually have a noticeable chance of a prediction. So eventually, in some epoch, we make a prediction because we have this sequence of nice epochs that are our friends. All right? So our algorithm is brave enough to make a prediction at some point. Now the question is whether it's smart enough to make a correct prediction.
The T star could have been picked in the last half of
Probably doesn't matter.
Yeah, so I mean, there's other times here where maybe we had no courage, but as long as we pick something within this pyramid, we have some decent chance. OK, so the key idea is to compare the odds of making a correct versus incorrect prediction. We're going to analyze the contribution of every chip on our stack. So just fix attention to some chip here, which we can graph over time. It lives on the stack. Do you have a question?
Would you mind going back and just, I missed the actual function at the current term.
Sure, the probability of. Sure, I'll just write it out for reference.
Actually, can I ask another favor?
Sure.
Could you write it in a
Different color? Yeah, absolutely. How's that?
And D is just
So-
a parameter?
So D is, remember that this P we chose was, so P over D is an approximation to epsilon. So think of epsilon as P over D.
There was any reason not to make epsilon 1 over d?
To make epsilon, so we don't have control over epsilon. Epsilon is our initial assumption.
I know, but d
Oh,
is free. This
so-
is
So,
make p equal 1, d equal 1 over
oh, yeah, sure. Yes, so for,
one less parameter.
that would be one less parameter. Good suggestion, thank you. OK, so we've come back to this chip, and we're analyzing its contribution to the success and failure probabilities. OK, so as long as this chip lives on the stack, it's giving us some courage, and that's contributing directly to the probability of making a guess about this bit, and this bit. So in this particular chip's case, we have 2 successful predictions that it's contributing to and 1 unsuccessful one. And the intuition for this analysis is that there are really 2 at least extreme cases that are both that we're satisfied with in either case. First, if a chip remains on the stack for a very long time, where I'm being vague here, then the fraction of 1s during that interval shouldn't be too large. It should be at most P over D. And why is that? Well, if more 1s came along, they would have driven the chip off sooner, just by the way that chips are added and subtracted. Okay? So in this case, we're happy because the fraction of incorrect predictions it's contributing to is on the order of is just epsilon. Okay?
So this is supposed to be for which chip? Probably the.
This is- This is for chips that stay on the stack for a very long
it's
time.
long enough.
So I'm not even going to quantify it because this intuition is not going to actually have to function in the proof because you'll see. But this is how I was able to feel confident in this approach to the problem. On the other hand, we have chips where this doesn't hold at all. So for instance, if you have a chip that is placed on the stack and then immediately driven off by a 1, then it's really only contributing to a failure, to a false prediction of a 0. And that's no good. But by its very nature, it was put on the stack and immediately removed. So the amount of false courage that it's given us to make false predictions is small. And so we should hope that the total summing over all chips should also be small. But thankfully, we don't have to do any kind of case analysis. We can just analyze all of our chips in a really simple and unified way. So again, fixing attention to this chip C, let's let zeros of C and ones of C be the number of zeros and ones that it contributes to predictions on. So here, the zeros of C would be 2, ones of C is 1. And so we can very cleanly express the contribution of chip C's, the contribution to the success and failure probabilities as such, where we're assigning, we're dividing up the contribution in the obvious way. Okay, so you have this kr squared term in the denominator, which reflects the fact that first, the probability of making a prediction, given that you've chosen that time, is on the order of 1 over is the height divided by the kr parameter, but we also have to choose this as the critical time. And the claim now is that we have this simple inequality between zeros and ones of C. And why is that? Well, this left-hand side reflects something natural. Namely, every time we see a 1, we subtract at most q, and every time we see a 0, we add exactly p chips. So this is actually an upper bound on, or rather it's upper bounded by the loss in stack height when you compare the time immediately after C was added to the stack and immediately after it was removed, if it was removed indeed. And C was removed along with at most q other chips. So this is upper bounded by q. So there we have it. And now this is related to the success and failure probabilities. But let's just go through that. So let's just sum that over all chips C. And we only add at most p times the number of steps chips in total. So we get this bound up here. Let's just divide by p. And then by this normalizing, or this factor that we encountered earlier. And now this can just be re-expressed as q over p times the failure probability overall in this epoch minus the success probability. And I made a typo here. This should be, yes, 1 over kr, which we've chosen to be on the order of r negatives squared. So there you have it. That's really the idea of the proof. So we haven't been able to directly compare the success and failure probabilities over an individual epoch, but we've been able to compare them modulo a small error term that pops in that we can control by making the epochs suitably large. So using this technique, or using this result really as a black box in the paper, we also give a bit prediction algorithm that works under broader classes of assumptions that are at least modeled on this initial one. So we can predict a bit, maybe a 0, maybe a 1, under the assumption that some certain word appears only rarely. Okay? So these results have to be a little bit quantitatively weaker to hold true. For instance, suppose that some word like a sequence of 10 zeros occurs only a 30% chance of the time. Does it follow that we can predict a 0 or 1 with something like 70% success probability? Well, no, because if we just flip a sequence of random 0s and 1s, we let that be our sequence, we're certainly going to have a sequence of 10 zeros be rare. It's going to be geometrically rare in the length of this word, but we can't make any non-trivial predictions with success probability greater than 1/2. So you get some loss, but
is there a notion in which the loss should be related to the entropy with which, the probability would normally associate with that compared to?
So there probably is something of that flavor. So reiterating what I said, the statement that I made in the paper is that if you have a finite automaton that's processing some infinite sequence, and you assume A that something like it has a strongly connected state space, and you also assume that some state of that automaton is visited only rarely on the input sequence. So this is a class of binary sequences we could consider. It follows from that we can predict a 1 with some success confidence, a 1 or a 0 in our sequence. And now the statement is weakened by the number of states in our automaton, and it's kind of geometrically weakened by that. And you can show that.
Do you have a lower bound that it?
Yeah. So basically, you can turn this word problem into a finite automaton. That basically has, if it's a string of 10 zeros, it would have 10 states, and so you get this geometric weakening of the.
So I guess what I'm saying is, it's natural to think that it would geometrically decrease with the number of states, but also that depends, as from your discussion, on what the probability bounds you have versus the chance it would occur in some string. Do you have, so lower bounds which are actually dependent on those that the upper bound is?
That are just based on the probability of occurring in a random string?
Predict, it's an adversary running the show. So you can always predict, if you are allowed to predict both 0 and 1, you can predict the probability half always. You're talking about the probability of it occurring, the probability of it occurring can be.
No, but how much you can be bounded away from half based on what constraints you have, right? So, the constraints will depend on how the probability, the bound you have on the frequency of occurrence of some particular substring is related.
In a truly random string? In a truly random sequence?
Yeah,
or?
for example.
Okay.
Right?
Let's talk about this offline. Okay. I think that there's probably more to be done there if you'd like. Sure. So I also do more work on this ignorant forecasting problem, in which we make no assumptions whatsoever on the input sequence, and we find that we can actually still make certain kinds of predictions very confidently. So again, now we have no control over x whatsoever, and what we're going to want to do now is choose an interval of time of unseen bits and predict confidently and accurately the number or the fraction of 1s appearing in this interval. Okay. So I was surprised by.
We get to pick the interval.
We get to pick the interval. Yes. So you're anticipating me here. If it was a fixed interval, we'd have no hope. But we get to choose not only the position but also the size of the interval that we're going to be choosing. Okay. So an interval forecaster algorithm just makes such a prediction with freedom to choose p and n. And so we claim that for any epsilon and delta, there is an ignorant interval forecaster that's accurate to plus or minus epsilon with high success probability 1 minus delta. And in this case, we don't actually even have to, the adversary can't even push us back in making our prediction. We have a schedule that we can run on. And in this algorithm that I'll present, it runs in time exponential in 1 over epsilon and 1 over delta. So here's the approach. Let's just think of x now as being a finite string of length 2 to the n, and we're going to stick it on the leaves of a binary tree. Here's what we do. Again, we have this value t star that we're going to be using. Maybe I should have chosen a different symbol, but it's going to be some uniformly selected, basically, height in the tree, some depth in the tree. Then we're going to take a random walk in the tree of length t star, ending up at some vertex. Okay, so here it is. This is all conceptual, because I mean, what the algorithm is actually doing is just looking at bits of the sequence one by one.
So when you say take a random walk, do you mean always going down? So picking
A random directed
point
walk.
at that level,
Yes.
or-
So we're taking a random directed walk from the root of length t star.
Okay. So say
Just
that-
uniformly pick a node in
then
this
trace
star
that.
height.
Of t star height, yes, exactly.
Okay.
And so then we make the prediction that the fraction of ones in the right subtree of this node is just going to equal the fraction in the left subtree. Okay, so in this case, we observe the sequence up to this point. We observe that this subtree contains only ones, then we guess that this is going to be a 1 as well. Okay. So why does this work?
So you're not using actually the information you have in the
Most of the information we're throwing away. We're only looking at this subtree, yes.
main decision is the size of the interval, and then you say the right half will be the same as the left half.
Exactly. So it's an interesting question whether you can use more information in the sequence to do quantitatively better for this problem. So I'll mention that again. So how do we analyze this algorithm? Well, the first idea is to take our random walk that ended at a partial, an intermediate vertex, and just extend it conceptually to a full random walk. Okay? So in this case, our random walk would have extended to one of those leaf nodes. And let's let x sub t be the fraction of ones appearing below the tth step in our walk. So x sub 0 is just the fraction of ones in x itself, and so on. It's a martingale. And, and what I'm actually going to show you is strongly influenced by discussions with Russell years ago on properties of martingales, so on thinking about different things. So thank you, Russell. So again, we have a martingale that is conditioned on x of t. The expectation of x of t plus 1 is exactly the same as our current value x of t. And it follows from some basic manipulations that for any t greater than s, if you look at the difference of the value between the tth plus first and tth steps, this is independent of, in this sense, the difference between the s plus first and the th step.
So why do you need t greater than s? I mean, it's symmetric in t and s.
Right, as long as they're not equal.
Yeah, they are not equal. So
And by some more manipulations, we get the following. So if you look at the expected squared differences between the final step and the initial step, well, on the one hand, certainly that's at most 1, because these are just fractions. These are between 0 and 1. But now you can also sort of reverse telescope this. This is equal to xn minus xn minus 1 plus xn minus 1, and so on. And so you have these terms which are being expanded after you square. And using this previous property, most of these things cancel out. And so what you're left with is just this sum. And so you can bound this sum by 1. And so looking at this, what does this tell us? It tells us that regardless of the initial sequence x that we're basing our martingale on, if you choose if we divide by n, if you choose a random time t, and you look at the difference between the martingales, values between the t and t plus first step, the expectation is quite small. Okay? Yeah, 1 in root n, because we have this quadratic factor creeps in.
And taking like majority vote is about the extreme example. 1 in root n almost all the time.
the majority of the left and right terms of
So just restating the inequality here. The claim now, is that if this increment, this difference between the martingale values at this point is small, then t is actually would be a good choice for us as our random place to stop, t star. Okay, because if the fraction doesn't change too much from this point to this point, that means that the fraction in these two subtrees.
From that point to that point.
Well, I guess in this illustration rather it's here. But if in this case, if the change in the martingale value from here to maybe we extended the step here was small, that would be because the fraction here is nearly the fraction there. Okay. And through some very very simple technical work, you get the bounds that I quoted for n. Okay, so I'll finish with some open questions. First, can we characterize the sets of sequence sets A for which this kind of confident zero prediction that we described earlier is possible? So epsilon weak sparsity was enough, but it's certainly not sufficient. You can contrive other kinds of examples where you can study this problem. And in this earlier work on gambling and the problem of making a fortune over time, there was this very nice kind of geometric characterization of the winnable sets A, the sets for which you can win at gambling on A. But I don't know of anything here, and I think that would be nice to look for. Another question would be to find an interval forecaster like the one I just described, but that has a better runtime. It didn't need such a long sequence. And I think that just as applied math, right? This could be a fun party trick to perform, but the length of the sequences that you need is astronomical. So that's unfortunate. You could use cards, for instance, to implement this.
But you don't have any drawbacks.
No, except for what follows from basically considering the random case. And now, the next two questions I kind of thought of recently while just thinking about the slides, so they could have easy answers as far as I know. So suppose we have some distribution over possible sequences for our zero prediction task. And suppose that it's easy to solve our zero prediction task on this distribution. But maybe somebody else doesn't believe that this is the distribution governing nature. And we'd like to have a more conservative assumption under which we can still succeed. So is there a generic procedure modeled on the specific procedure in this work for deriving some supporting set A on which you can still succeed based on D? And a related question is kind of like, can you go in the other direction? From a hard set A, where zero prediction is hard, can we derive some hard distribution over A, which is kind of the hardcore, or the worst possible instances from A? So if you're trying to argue to somebody that a prediction task is hard, but they're Bayesians or they have a distributional worldview, can you provide evidence for them from the distributional world? So and that would just be going the opposite direction. And I'd mentioned that this would also give an alternative and non-constructive proof of our possibly non-constructive proof of the main result. Because if you have any distribution that's supported only over these epsilon weakly sparse sequences, well, if you just follow it out and you wait and you update your posterior distribution based on the bits you've seen, at some point you're going to have to reach a point where the conditional probability of a 1 on the next step under this distribution is very small. If that didn't occur repeatedly, then you would never reach an epsilon weakly sparse sequence. And so we'd actually be able to, to boost from that basic observation about distributions over epsilon weakly sparse sequences to a result about all sequences. So that could give a more general and powerful tool to derive these, worst case prediction algorithms. And again, these two last questions, I just should have thought about them earlier, but maybe they're quite tractable, or maybe they're easy counterexamples. So thank you.